Let's solve the following system of linear equations. 2x minus y plus 3z equals 5. 3x plus 4y minus 3z is equal to negative 6. And x plus 2z is equal to 6. And there's many different ways to do these problems. But I am going to do an unusual way. I'm not going to do this like you did in beginning algebra or intermediate algebra. I'm actually going to solve this mimicking a procedure called elementary row operations. The first thing I'm going to do is actually label my equations. I'm going to label them like this: equation 1 being the top equation, equation 2, and then equation 3. So what we're trying to do is find values for x, y, and z that will satisfy all equations simultaneously, and it will make all the equations true all at once. That is the goal. We're trying to find the missing values x, y, and z that will actually satisfy all three equations. I am going to mimic a procedure that you may end up learning later on that involves matrices and elementary row operations. So the first thing I'm going to do is I'm going to switch equations 3 and 1. And then we'll rewrite the system in this order. X plus 2z is equal to 6. And then equation 2 is still equation 2. And then now the equation 3 is simply 2x minus y plus 3z is equal to 5. Now you're probably wondering, why did I do that? Let me rewrite the first equation really quick. So now this is a little bit different. I'm going to relabel this. This is now equation 1, equation 2, and this is now equation 3. What I'm going to do now is actually temporarily eliminate x in two of the equations. And the way I'm going to do that is I'm going to apply negative 3 times equation 1 plus equation 2 hang on just for a sec here. I'm going to do that. And we're also going to use negative 2 times equation 1 and then add it to equation 3. I'm going to keep equation 1 where it is. So equation 1 is still going to be called x plus 2z equals 6. Let me move this slightly over. Move this over here. It's actually much easier to do this with matrices, but we are not there yet. So I'm trying to reorganize my paper here. Need this a little bit higher, right about there. Okay, a little bit more to my right. There we go. I think I finally got the spacing right. I apologize. I'm not used to doing this without matrices. It's much easier with matrices. And this is going to be something else. This is going to be something else. All right, what is negative 3 times equation 1 plus 2? What does that mean? I'm going to do this once off to the side. So I'm doing a lot of steps in my head. Negative 3 times equation 1 plus 2 really means you're going to take negative 3x plus well, let's do minus 6z is now equal to negative 18. So that's negative 3 times equation 1. Now plus 2, well, what's equation 2? This is equation 2. 3x plus 4y minus 3z is now equal to negative 6. And then you simply add these vertically. And so that's why this plus sign is here. So you do negative 3 times equation 1, which is just saying negative 3 times x plus 2z is equal to negative 3 times 6. So that's the negative 3 times equation 1 part. And then you simply add equation 2 to that. And what happens then, you get this new equation, and I'm going to put it right here. You're going to get 4y minus 9z is now equal to negative 24. All right, and that becomes our new equation 2. So that is our new equation 2. In a similar fashion, we're going to get a new equation 3. We're going to store it in the third row. So we're going to do negative 2 times equation 1 and then add it to equation 3. So we get 0 times x. And then we get negative y. So the first thing we see is negative y. And we need negative 4z add a 3z. Negative 4z add a 3z, we get minus z. And then we also have negative 12 add 5. Negative 12 add 5 is negative 7. All right. We're going to do one more thing. We're going to do one more thing here. We're going to do 4 times equation 3. We're going to do 4 times equation 3. And then add it to equation 2. And then we'll store it. We'll store it where? We'll store it in the second row. So we call it 2. Now, what's our first row? We're not even touching the first row. X plus 2z is equal to 6. That is our first row. Once we get 4 times equation 3 and add it to equation 2, what happens? Well, we get 0y, and then we get negative 4z minus 9z. So negative 13z. And then we also have negative 28 added to negative 24. So negative 52. Yeah. And then we did not change equation 3 at all. So equation 3 stays the same. I should draw another wiggly line here. There we go. All right. So equation 3 stays the same. Negative y minus z is equal to negative 7. So what I did was I ended up working this idea of adding over and over again to eventually get down to one variable. And that is actually equation 2. We're actually going to take equation 2, and you could easily see that 13 is not 0. So if you divide both sides by 13, or negative 13, we get z equals 4. And then once you get one of the numbers, it's a lot easier to get the other numbers. So if you look at equation 3 from here, we can get y. That is going to be 7 minus y. Z is equal to 7 minus y. But we know what that is. That is equal to... Oh, why did I solve for z? I apologize. I meant to solve for y. Let me slow myself down. Let's solve for y instead. So I get 7 minus z. Y is equal to 7 minus z. Yes. And we already know z is 4, so this has to be 3. And then we go back to equation 1 to get our x. X is equal to 6 minus 2z. And we know what z is. Z is 4, so x is negative 2. So is there a solution to this system of equations? In fact, there's only one solution. And we're going to put that in a solution set. The solution set consists of one ordered triple. So there's only one solution, and that one solution is called an ordered triple. It's not only just one solution, it's actually what we call a unique solution. And what does the word unique means in mathematics? It just means one and only one. Unique just means one and only one. It is the one and only one solution to this system of equations. So this is the set consisting a unique solution. Solving a 3x3 system of linear equations. Consider the following system. There's an equation 1, equation 2, and equation 3. I'm going to go ahead and label that in that order. The first row is equation 1, the second row is equation 2, and the third row is equation 3. And I'm actually going to solve this in such a way where it would actually prepare you for the study of matrices. And with matrices, there's something called elementary row operations. So I'm actually going to mimic some of those operations here. One of the key things is that we're going to use the addition method. We tend to add our equations as much as possible. What I'm going to do now is actually I'm going to rewrite the system. And the first thing I'm going to do is actually rewrite equation 1 on its own. I'm going to rewrite it right here. Equation 1 is going to stay the same. 3x plus 2y minus z is equal to negative 5. I am going to rewrite equation 2 though. I'm going to do something a little different. I'm going to write negative 1 times equation 2. So I'm going to take negative 1 times equation 2. I'm going to take negative 1 times equation 2 and then store it as a new equation 2. So if I do that, look at the original equation 2 and multiply both sides of that equation by negative 1. We're going to get x plus y minus z is now equal to negative 1. I'm going to leave equation 3 alone. Equation 3 stays the same. 5x plus 4y minus 3z is equal to negative 5. Now I'm going to switch equations 2 and 1. And you might think this is a lot of writing, but for now this is okay. I'm going to switch equations 2 and 1 and relabel them. So I'm going to switch equations 2 and 1. So I'm going to indicate that with this double-sided arrow. Switch equations 2 and 1, or 1 and 2. So equation 1 is now x plus y minus z is equal to negative 1. Now what's equation 2? Equation 2 is now 3x plus 2y minus z is equal to negative 5. And equation 3 stays the same. And now I'm going to do some pivoting action. I'm going to do a little bit of a pivoting action here. I'm going to keep the same equation 1, which is x plus y minus z is equal to negative 1. And I'm now going to do negative 3. I'll write this in a different color. How about that? I'll write it with the previous color. I'm going to do negative 3 times equation 1, add it to 2, and store that as a new equation 2. I'm also going to do a negative 5 times equation 1 plus equation 3 and store that as a new equation 3. And you're probably wondering, what am I really doing? I'm actually temporarily eliminating x. I'm going to temporarily eliminate x from the system, at least for the second 2 rows or the second 2 equations. So when you do negative 3 times equation 1 plus equation 2, you're going to get 0 times x, which is 0. You're also going to get negative 3y plus 2y. Negative 3y plus 2y. So you get negative y. And I'm going to get how many z's? I'm going to get 3z, subtract a z. So plus 2z is equal to a 3 plus a negative 5. Negative 3 times equation 1 will give you a positive 3 plus a negative 5. So that's a negative 2. Now we do the same thing for our new equation 3. Negative 5 times equation 1 plus equation 3. We get 0 times x. We got negative 5y plus 4y, so we get negative y. And then we have 5z minus 3z. So we get plus 2z is now equal to, looks like we got 0. Yes, we got 0. It's now equal to 0. All right. Now from here, I'm going to move over here and reorganize this system again. I'm going to keep the same equation 1. Let me move that over a little bit. I need to save myself some room. Keep the same equation 1, which is x plus y minus z is equal to negative 1. Now I'm going to perform a negative 1 times equation 2 and add it to equation 3. I'm going to do a negative 1 times equation 2 added to equation 3. I'm going to put that into the new equation 3. Relabel it as the new equation 3. I'm going to keep the same equation 2. Negative y plus 2z. Be a little bit more organized here. Negative y plus 2z is equal to negative 2. All right. The third equation now is, we get 0 is now equal to 2. We all know that is false. This is not possible. We know 0 does not equal 2. So 0 equals 2 is a false statement. Therefore, there is no solution. No solution to the system. Another way to write that with mathematical symbols is simply write a set race with space in between, and then close it with the right hand set brace. This right here, this little picture, is called the empty set. So I'll repeat it again. To show this symbol, we need a left set brace, provide empty space, and then write the right set brace, and we call this the empty set. So if you symbolize your final answer with the empty set, you're really implying the words no solution. And we always say no solution to the system. So I'm going to go ahead and circle the final answer. But more importantly, make sure you can actually show organized work. Notice how neat this is. All your x's are in one column, all your y's are in another column, all your z's are in another column. Your equal signs should pretty much stay right below each other. And then you have, the number on the right-hand side of all these equations, or the right-hand side of the equal sign, should also be in a column. Notice every time we rewrote the system to have 3 equations. Every single time. So this is to actually prepare you for another tool called matrices. And so that's why I'm doing it in this sort of this new method that you may have never seen. All right, that's it for now. Solving a 3x3 system of linear equations. Consider the following system. Negative x plus 2x minus 3y plus z equals 4. Negative x plus 5y minus z is equal to negative 1. 5x minus 4y plus 2z equals 11. The first thing I'm going to do is actually label all these equations, or label all these rows by 1, 2, and 3. I am going to solve this using the style of elementary row operations, which will actually help you understand the tool of matrices later on. So I'm actually going to rewrite the system, or rewrite an equivalent system every time, using some operations that involve addition or switching of 2 rows, or multiplying 1 row and adding it to another row. The key now is to really keep things organized. The first thing I'm going to do is rather simple. I'm actually going to take equation 2 and multiply it by negative 1. So I'm going to keep equation 1, which is 2x minus 3y plus z is equal to 4. I am going to multiply by equation 2 by negative 1. That means I'm going to multiply both sides of equation 2 by negative 1. And we're going to store this as the new equation 2. And if I do that, I get x minus 5y plus z is equal to 1. I'm also going to keep my original equation 3. So equation 3 doesn't change either. It's simply going to be 5x minus 4y plus 2z is equal to 11. So as you're taking notes, make sure you understand how neat this is going to be. Everything is going to be very organized. It's not only going to be organized in rows, it's going to be organized in columns as well. Now I want this leading x right here, because it actually has a leading invisible 1. We would really like this in the first row. So now I'm going to switch equations 2 and 1, and we do have a mathematical symbol for that. We are simply going to write, take 1 and do a double-sided arrow and switch with equation 2. And now our new equation 1 has changed. It's going to be x minus 5y plus z is equal to 1. Our equation 2, our new equation 2 has changed as well. And our equation 3 has remained the same. 5x minus 4y plus 2z is equal to 11. Now that we have the leading 1 in the very first row, we are going to keep the first row. So I'm going to first take equation 1, take that same equation. And now we're going to use the addition method that involves equation 1 and 2, and the addition method that involves equation 1 and 3. So we're going to temporarily eliminate x. What does that mean? I'm going to take negative 2 times equation 1 and then add it to equation 2 and then store this in our new equation 2. If you do that, you get 0 times x, and we get 10y minus 3y, which is 7y. We also get negative 2z plus z, which is negative z. And we also get negative 2 add 4, which is positive 2. In a similar fashion, we're going to perform the addition method for equations 1 and 3. So we're going to do negative 5 times equation 1, add it to equation 3, store in this new equation 3. If we do this, we get 0 times x, and now we get 25y minus 4y, so that's 21y. We also get negative 5z, add it to 2z, so we get negative 3 times z. And then we also have negative 5 added to 11, which is 6. So at this point, what you want to realize is how organized things are. Look how organized things are. All the x's are in one column, all the y's are in a column, all the z's are in a column. Everything's labeled with 3 equations, 1, 2, and 3, 1, 2, and 3, 1, 2, and 3. So every time we rewrite the system, we tend to write all 3 equations. Now I'm going to look for patterns. There's a pattern with equations 2 and 3. It's hard not to notice it. I'm actually going to do something called, I'm going to do negative 3 times equation 2 and then add it to equation 3. First thing I'm going to do is keep the same equation 1, x minus 5y plus z is equal to 1. We're going to keep the same equation 2, 7y minus z is equal to 2. However, we are going to change the equation 3 by doing negative 3 times equation 2 from the previous equation 2 to previous equation 2. I'm actually doing this part right here. Negative 3 times equation 2, and then add it to equation 3. And then where are we going to store this? We're going to store this as the new equation 3. If you do that, you get 0 x's, and then you're going to add 0 y's. Yep, you get 0 y's. So the only thing left we have is positive 3z plus a negative 3z, so we get 0. We get a 0 over here is now equal to 0. Well, that's true no matter what. That's true. We already know that. So this is not any new information. This also tells you that the system is consistent. In other words, there will be solutions. And not only does this system consist of solutions, and the solutions are dependent. So this is a system that is consistent and dependent. The emphasis here is consistent and dependent. So we have a system that is consistent and dependent. Let's find that dependency relationship. It's not going to be too hard. What we want to do is realize that y depends on z. Z right now is our free variable. So we certainly could solve for y. So if you take our y, so take your equation 2 and solve for y. Y is now equal to z plus 2 divided by 7. There's your y. You could also write this as what? 1/7 z plus 2/7 if you want. You know, this looks like mz plus b. So this looks like a straight line in the yz plane. Let's look at x now. Well, we know y is dependent on z. Well, x is dependent on y and z. So can we find x? Let's find out. So I'm going to go back to equation 1. What we're doing right now is something called back substituting. We're going to go back to equation 1 and solve for x. X is now equal to 5y minus a z plus a 1. But we know what y is. 5 times 1/7 z plus 2/7. Here's my y. We need to subtract a z, so 7/7 z. Might look a little confusing, but that says 7/7 z. I just subtracted a z, and then we're going to add 1. So how many z's do we have? We have negative 6/7 z and then plus 3/7 after finding common denominator. Oh, I take that back. We have 10/7 plus 7/7. 10/7 plus 7/7 is 17/7. Let's try that again. That should be 17/7. All right. So really, all our solutions are going to be dependent on x. Let's write our set of solutions. We have our final set of solutions. It's going to be the set of ordered triples of the form negative 6/7 z plus 17/7, comma. Where's our y? Y is 1/7 z plus 2/7. And then what's our last representative? Our last representative is z, parenthesis. Then we write this bar. This bar is read as such that z is a real number. So every ordered triple that satisfies the system of equations has to have these kind of relationships. Your x value is very, very specific, but you actually have to have this kind of pattern. Now, your dependent variable could have easily been y. So you actually had two choices here. Notice for equation 2, you could have solved for z instead of y. And if you did that, you're going to get some different patterns here. You wouldn't have z anymore, you would have y. You wouldn't have y's here in every position. But in the end, it's going to represent the same ordered triples. There's actually an infinite number of solutions here. A good solution to probably look at is let z equal 7. If you let z equal 7, you're going to get an ordered triple that satisfies all three of these equations. If you let z equal 7, you'll get an x value, a y value, and a z value that will satisfy all three of those equations. What's another good z to pick on? I would pick z to be 0. If you pick z to be 0, you'll also get an ordered triple that satisfy all three of these equations. Now there are lots of choices for z. How many choices? Well, z is any real number. So if you really want to emphasize how strange this is, you want to let z to be any real number. So let me add the word any in here. Z is any real number. The key to solving these systems of equations is be very, very neat. Notice if I had more space, my x's here would line up with the original x's. So notice the x column always is in the x column. The y column is always in the y column. The z column is always in the z column. And then the numbers over here are also in a column. We always write three equations in all these systems until you get to the end. Until the end, we get kind of sloppy. We go back substitution, and then we actually find the ordered triple. But 1, 2, 3, 4 times I wrote the system with 3 rows or 3 equations. So keep that in mind. You're trying to write the system over and over again with new labels. And then eventually we back substitute and we get our ordered triple. Let's circle our final answer. The system consists of infinite number of solutions, and the solutions are dependent. So this system is consistent and the solutions are dependent. Solving a system of linear and quadratic equations. The first equation is quadratic, 3x squared plus 2. That's a U-shaped graph that's opening up. The second equation here is linear. This is actually in standard form. 9x plus y is equal to -4, or you could call it a times x plus b times y is equal to c. That's what we mean by standard form, where capital A is greater than 0. That's not very important. The idea right now is to find the point of intersections of these two graphs without actually having to graph them. So there's really two equations here, and we're trying to find when do the x values, x and y values, satisfy both equations simultaneously. Why don't we use the substitution method to do this? I'm going to go ahead and label this as equation 1 and the second equation as equation 2. We're going to sub 1 into 2. And what do I mean by that? Every time you see a y, you're going to write, every time you see a y in equation 2, you're going to write parentheses 3x squared plus 2, right? Whenever we write our substitution, usually indicated with parentheses to substitute that quantity. Now we could simplify this. Notice there's an invisible 1 in front of those parentheses, so you could distribute this invisible 1 and the parentheses drop off right away. So we get 3x squared plus 9x plus 2 is equal to -4. And now this looks like a classic problem that you probably have done in algebra many times, maybe even hundreds of times. And why don't we try to factor this? We could use the trial and check method. Some of you might like to use the diamond method or the AC method. I'm a big fan of trial and check, as long as you are playing with these letters or numbers correctly. So we need to make a positive 9 there. Well, this doesn't factor. And why doesn't it factor? Well, can you figure out there's a mistake in the procedure? So that's why this is not factoring. I could have tried the quadratic formula, but the more I look at this, I realize there is a mistake. And the mistake is right here. This shouldn't be a subtract 2. This should be a positive 6 or a plus 6. So why don't we fix that? That should be a plus 6. And let's, of course, take our handy dandy eraser and clear that out. And now we have a quadratic equation, But every term has a 3 in it, so make sure you know how to factor. Let's take out the greatest common factor, which is 3, and we have x squared plus 3x plus 2 equals 0. And then we have 3 times x, let's say x plus 2, and then x plus 1. I've checked my factoring. There are 3 factors here. Obviously, 3 is not equal to 0, but we do get x equals to negative 2 and x equals negative 1. Make sure you remember to write equals 0 on the previous line. Make sure you write that equals 0. This problem is really about equations, so you're going to write a lot of equations. Now we're going to go back and substitute. We're going to substitute and try to find y. So we're going to use equation 1. Equation 1 to find y. So let's say for x equals negative 2. We're now going to use a substitution method. So y is equal to 3 times the quantity negative 2 squared plus 2. So what is our y value? That's going to be 14. What about the other x value? For x equals negative 1, we're still going to use equation 1. And we're once again going to use a substitution method. So y is equal to 3 times what? Negative 1 squared plus 2. And that is 5. So what does our final answer look like? Our final answer is actually going to be a solution set with 2 ordered pairs. The first ordered pair, it doesn't matter here, there's no order to this. But let's say I'm going to list the first ordered pair as negative 2, 14. And let's list the second ordered pair as well. We need parentheses. Negative 1, 5. And then close it with a set brace. So this is a set that consists of 2 solutions or 2 ordered pairs. Circle your final answer. Make sure you show all your work nice and neat, and sort of just react to these algebra problems. Let's solve the following system of equations. There are 2 examples here, A and B. We'll go ahead and do example A. The first thing I'm going to do is actually label the equation. I'm going to call the first one equation 1 and the second one equation 2. Now the first one has a nonlinear equation and a linear equation. What we're going to do is take that linear equation, which is equation 2, we're going to sub 2 into 1. The first thing though, even though I'm going to sub 2 into 1, I got to rewrite equation 2. So maybe I won't label that as equation 2. I am going to label the first one equation 1. I'm going to rewrite the second equation to be y. You can easily see that you could write y by itself. So that would be 3x plus 4. I'm going to call this equation 2. And I'm still going to sub 2 into 1. But now I'm just going to do it a little bit later. So I have equation 1, I have equation 2. Now I'm going to sub 2 into 1 because I have y by itself. So for equation 1, whenever you see y, put parentheses. X squared plus y. Well, y is going to be in parentheses, and y is going to be 3x plus 4. Quantity squared is equal to 8. And now you could react to this as if it was an algebra problem, as if you have been solving quadratic equations for most of your life. So here we go. Is equal to 8. And of course, for quadratic equations, we would like to set the equation equal to 0. So let's try 10x squared plus 24x plus 8 is equal to 0. There is a greatest common factor here, so let's factor out a 2. So we get 5x squared plus 12x plus 4 is equal to 0. Now we're going to factor this. I like to use trial and check. Luckily 5 is a prime number, so we could use 5x there. Can we make 12? I believe so. Put a 2 and 2 here, and then put a plus and plus here. And I did check my factoring. That is correct. This is now equal to 0. Now 2 is a factor that's not equal to 0. However, we do get x equals negative 2 halves. I'm sorry, negative 2 fifths. Or we get what? X equals negative 2. So how do we get our y values? Well, then we go back to equation 2. So I'm going to bounce off of equation 2 here. And let's solve for y. So the first y is when, let's say, when x is equal to negative 2 fifths. Can we get y? Yeah, of course we can. That's negative 6 fifths plus 20 fifths. So y is going to be equal to 14 fifths. Let's try to get another ordered pair. How about when x equals negative 2? We're still going to use equation 2. So y is equal to 3 times negative 2 plus 4. So that is now equal to negative 2. So for example A, we have a set that consists of 2 solutions. We actually have a set with the ordered pair, negative 2 fifths, comma, 14 fifths. And then the second ordered pair, I'll separate it with another comma. We'll put parentheses, negative 2, comma, negative 2. Close with a set brace. I'm going to repeat this again. This is a set that consists of 2 solutions or 2 ordered pairs. I'm going to circle that as the final answer for example A. And let's proceed to example B. Now, for example B, both equations are nonlinear. And you can see they're both nonlinear because there's actually a square or an exponent of 2 on your variables. So both of these are nonlinear equations. But the first column has a like term and the second column has a like term, which tells us we should actually use the addition method. I am going to do something a little bit different. I'm going to take the first equation and I'm going to multiply it by negative 1. If you do that, you get negative x squared minus y squared is equal to negative 10. So multiply both sides of the first equation by negative 1, you get that. I'm simply going to rewrite the second equation, x squared plus 5y squared is equal to 6, and now we're ready to do the addition method to our new equations 1 and 2. We get 4y squared is equal to negative 4, and we divide the entire sides by 4. We get y squared is equal to negative 1. Uh-oh. Well, guess what? We're trying to keep these solutions in the Cartesian plane, or in the real number two-dimensional system. Okay, remember your axes that you're looking at, these are in the xy plane if you were to graph these. So right now we have 4y squared is equal to negative 4. Well, that is bogus. In other words, there's not possible to get a y value here. Y is equal to a complex number, and we know that plus or minus I is not real, or not a real number. So this is not a real number. In other words, that's going to imply us to conclude no solution. Even though you got no solution, make sure you're able to show all this work. All this work is necessary. Solving a word problem involving geometry using a system of nonlinear equations. The perimeter of a rectangle is 16 8/10 kilometers, and its area is 14 3/100 square kilometers. Find its length and width. Let's just draw a hypothetical picture. Picture of a rectangle. So we'll say the width is at the bottom. We don't know what it is. Let's just call it W. The length is the other side. So this is the length, and we don't know what that is, so we just call it L. All our units are in kilometers. And we do know that the perimeter formula is this. P is equal to twice the length plus twice the width. Right? The perimeter is 2 lengths plus 2 widths. And we also know that 16.8 is equal to 2L plus 2W. We also know that the area of a rectangle is length times width. But we're also given the area. It's 14.03 is equal to length times width. Now you got to pick on a letter here. I'm actually going to pick on solving for L. That is, we're going to write W is not 0. We don't want the width of the rectangle to be 0 kilometers. If that was the case, we would have a bogus rectangle. None of this would make sense. So since the width is not 0, we could divide the entire sides by W. You do need to write this down. Make sure you write why you're dividing by a variable. You have to state that that variable can never, ever be 0. Now we have L is equal to 14.03 over W. We're going to call this equation 1 and call this equation 2. And we're going to use the substitution method where we're simply going to sub equation 2 into 1 and see what happens. So whenever you see an L, we're going to put parentheses. We're going to write 16.8 equals 2 times L, but instead of L, we're going to write parentheses 14.03 over W plus 2 times W. Now we want to clear fractions. So in order to clear fractions, we're going to multiply the entire sides by W. So now we have 16.8 times W is equal to 28.06 and then plus 2W squared. And not a problem, this is a classic quadratic equation that we could set equal to 0. 2W squared minus 16.8W plus 28.06 is now equal to 0. Now, because we have decimals, don't even bother to factor this. Instead, we're going to use the what? Quadratic formula. Negative b plus or minus the square root of the quantity b squared minus 4 times the quantity a times the quantity c all over 2 times a. And we're simply going to substitute for w. Let's see. W is equal to the opposite of b, which is 16.8, plus or minus the quantity b. Quantity b here is parentheses, negative 16.8 square, quantity squared, minus 4 times a. What was a? 2. And what was c? C was 28.06 all over 2 times a, which is 2 times 2. Go ahead and have your handy dandy calculator out, and we are simply going to write an equation for w. We do have 16.8 here, plus or minus. Let's figure out what's underneath this radical symbol here. So go ahead and type some things in your calculator. And we simply get 5.776 all over 4. Let's take the square root of that 57.76 and see what happens. That becomes 7.6. So we have two equations now. W is equal to, we we have 0.4, 4, and then a 2, right? That's one of your W's. Let me double check with a calculator here since I have it handy. Yes, that's correct. Divided by 4, excuse me. Or we have what? 9.2? Yeah, 9.2 divided by 4. So far we have W is equal to 6.1 kilometers, or W is equal to 2.3 kilometers. Now, each of these W's can't happen both at the same time. So let's just pick on one of these. Let's pick on the first W. What happens when W is equal to 6.1? So when W equals 6.1, let's find L. How do we find L? We'll go back to the equation 2, where L is equal to what? L is equal to 14.03 divided by 6.1. Let's see what L is now. We get 2.3. And that is not a coincidence. This is what math will do to you. It will surprise you, but at the same time, it gives you some intuition on what's really going on. So, do we really need to write this one? And I think the answer, well, I think you know the answer. And the answer is we don't need to write that second with. The first with is enough. So, according to our picture, we really have it the other way. So imagine if you rotated this rectangle where the long side is now the width and the up and down side is now the length. So that's kind of what's going on when I'm checking this. Find the length, find its length and the width. The width is 6.1 kilometers and the length is 2.3 kilometers. And it really doesn't matter which one you call the width or which one you call the length, because you could simply rotate the rectangle 90 degrees to your right or left and you'll get the same set of numbers. Circle our final answer, but more importantly, make sure you could replicate the work. Replicate the evidence and all those math ideas that you've been studying for years and years and years and years.